Hello, everyone, and a very warm welcome to today's webinar where we are talking about chip design from academia to big business. And we have a very we have an expert panel here today. But before I introduce them, I would like to just give you a quick introduction to myself and Danish Sound Cluster. My name is Jeppe Lindegaard. I will be the presenter of today's webinar. And at Danish Sound Cluster, we are a community for sound innovation. And you can follow us on YouTube and LinkedIn for updates about webinars like this one. And after the webinar, the recording will be available on YouTube if you miss any of the action along the way. We facilitate webinars like this one, conferences, network events, innovation projects, startup programs, and study trips. So if you are interested in any of these things, definitely go sign up and check out our website as well for more info about these activities. We are very happy to have a partner on today's webinar, EDA Embedded, and we appreciate your help on today's webinar. So thank you for that. Now, in the audience today, we have a very nice, diverse crowd. A lot of students in universities, but also a lot of big audio companies. But what we're also very happy to see is companies outside the audio industry. So thank you very much for joining today's webinar. We very much appreciate you. So let me start with the introduction of today's panel. And Farshad Moradi, please welcome Farshad professor and section head at the Department of Electrical and Computer Engineering, Aarhus University. You have a PhD in nanoelectronics from the University of Oslo in Norway from 2011, and you are the director of ICELab, focusing on chip design for ultra-low power applications. You have published more than 150 peer-reviewed scientific papers, and you're the CSO of Cenexum. I hope I pronounced that correctly. And your main research interest is on low-power ASIC design for computing on the edge. Welcome to you, Farshad. And next in the panel, we have Anna Kirkegaard, founder of Existential AI, making medical devices smarter through ultra-efficient brain-inspired chips, drawing from your background at the Danish Board of Technology and a master's in business administration and philosophy. You drive innovation of the intersection of AI ethics and hardware development. You lead a specialized team in neuromorphic ASIC development, creating IP that improves medical device processing, and look to build strategic partnerships with leading medical device manufacturers. So I guess you are at the right place today. Thank you very much, Anna, for joining us.
Thank you.
And next up, we have Jørgen Krag Jacobsen, representing IC Works open source chip design. You have a broad experience in all phases of mixed mode analog integrated circuit development, with knowledge and skills that crosses traditional disciplines. Full custom analog and digital design, backend tasks, synth, place and route, verification, and silicon production. Thank you very much for joining us today, Jørgen. And unlike the rest of the people in the panel, you will not do a presentation, but you will be moderating the discussion at the latter part of the webinar. So if you have any questions out there, please send them to us in the Q&A, and Jørgen will take care of that in the discussion. Thank you, Jørgen, for joining us. Next up, we have Dennis Øland Larsen, the CTO and co-founder at Skycore Semiconductors. Dennis specializes in high-performance switched capacitor DC to DC converters, and you hold an MSc in electrical engineering and an industrial PhD from DTU and GN Hearing, focusing on power converters for hearing aids. With experience from ICE Power, Meos Audio, and GN Hearing, Dennis has worked on chip design for audio amplifiers, Delta Sigma A to D, AD converters, and DC-DC converters. At Skycore, you oversee technology and IP development of advanced DC to DC conversion chips for power modules, data centers, and battery systems. Thank you very much for joining us, Dennis.
Thank you, Jeppe. Good job pronouncing all those things.
Yes, that's putting me at hard work today. Last in the panel, Christian Westmark, PhD and manager at Analog IC Development at GN Group, where you manage the analog and physical IC design teams, driving the creation of next generation chipsets for hearing instruments. You also hold an MSc in electrical engineering and an industrial PhD from DTU and GN, focusing on integrated power converters for hearing instruments. That sounds almost like Dennis. So I guess you'll have a lot to talk about today. You also have experience in power electronics and integrated circuit design, having worked with ICE Power as well, Oticon Medical, and GN. Thank you very much, Christian, for joining today's webinar.
Sure.
All right, so before I will leave the floor to you, Anna, with the first quick little presentation about chip design, I would like to just open with a question here, because I have proclaimed chip design to be talk of the town in audio. But would you agree, and why? Maybe you, Jørgen, want to start?
Yeah, thanks. It is. We have a very high level of high-skilled people in the audio business here in Denmark doing ASICs. I was part of Mirror's Audio. We did a Class D amplifier. You will find it in a lot of hi-fi brands and high power boomboxes like Soundbox. And that actually is a legacy of a lot of the thing that was done by the hearing aid companies. We have 3 of them here in Denmark. We have 50% of the market share. So we are in a very strong position there, and that's a strong center of knowledge there.
Mm-hmm. And what about you, Farshad? Would you agree?
Yeah, definitely.
Since we have this new Danish chips competence center, that might be part of that.
Yeah, definitely, I agree. I mean, we have a world-leading ecosystem within audio. And yeah, of course, many of the works that we are doing is directly or indirectly applied to also this business, but also we in academia, we should think ahead and establish some collaboration with hearing aid company or other business to keep this position being ahead of this technology. And this is why we are here.
Yes. So the potential is big, and it's not just in the audio industry, I suppose.
Yes.
Yeah. Anna, Dennis, Christian, please feel free to chip in if you have anything to add.
Yeah, I mean, I can only agree with what's been said already, but I'd just like to highlight another example of this good academia and spin out the situation I was with Ice Power, where both Dennis and I have also been before. Another example of a company employing IC design in the audio stuff, formerly part of Bang & Olufsen. Yeah, but yeah, many good examples of strong audio and chip collaboration.
Yeah, I will. When I was about to start my PhD supervisor told me, like, do you really want to start doing chip design? Because you realize it's kind of the foundation of everything, and most people don't talk about the foundation. Like if you imagine a house, like you look at what's up on top of the foundation. But I think in recent years, people have realized that you have to have this foundation in a lot of different products. And it's basically, you can say, driving a lot of our modern technology. And I think audio is one good example where chip design has made a big impact and continues to be a big part of the business, and also the academia, of course. And it's an example of an application where it's you can easily end up needing the benefits that you can get in a microchip, such as high integration, and you need a very specialized set of features, which you might not be able to get with off-the-shelf components. So I agree, it should be probably the talk of the town.
Right. Thanks, Dennis. I like that picture of chip design being the foundation of the House of Audio. So Anna,
yeah,
you can chime in, and actually you are the first to do your presentation, so you can just take it from here if you want.
Yeah. I think like maybe also it's I want to say like the talk of Europe, at least, like to have like chip competences in Europe is something that is like really prioritized right now, because we want to be more like independent. So I think it's not only in the sound industry, but also like more on like a global scale or like international scale, that this is something that is a priority. Yes, I can go ahead also with my presentation.
Sounds great, Anna. Thank you for that perspective. And I will leave the floor to you.
Thank you. So my name is Anna Kirkegaard. I'm CEO and co-founder of Existential AI. So we are a startup working with chips for edge applications. We have been working on this for 2 years and are currently developing our prototype. So we want to have more AI at the edge, and there are many different reasons for that. It can increase the accuracy in your data if you filter your data. It can give you like better data to make better decision making if you use it in medical devices. And sometimes we need algorithms at the edge because we don't want to be connected to Wi-Fi, and we need to like have smarter devices. The way to do it right now is often that you need to make a specific chip for a specific application. And as many of you probably know, this can be costing a lot of money and take some time to develop. So what our solution is that we are making a chip that is running that is optimized for some specific brain-inspired algorithms that allow you to run really low-power algorithms at the edge, and then it's flexible, so you can update your algorithms and not your hardware. Basically what we're doing is we're being inspired from how the brain works. So if you look at like the brain and how much it computes, it uses the same amount of energy as it takes to have a light bulb lit, like an older version of that. And then if you look at the same amount of operations, like in a supercomputer, you need to have the same amount of energy to light up an entire village. So like our brain is extremely energy efficient, and there is a lot to gain from doing some computations more in the way like how the brain works. So that is basically the starting point from where the startup comes from. We met at something called the Human Brain Project, which is a really big EU project, me and some of my co-founders. And from this like knowledge about like the neuromorphic or brain-inspired computation, this is like where we started like our company. So this is our team. I'm on the business side and I'm the CEO. Then we have Francesco, who is our AI lead and on the software side, and Dimitri and Abir, who are both on the hardware side. And then we have, among others, Jørgen in our advisory board. We have some advisors who are like on the semiconductor side, and we have some advisors who are on the more like sales and business side. So some of the things that we've been doing so far, because when you're a startup, you kind of need to go in and figure out where do you belong in this market, like where do you get traction. So we've been like exploring some different applications. We've also been exploring some applications with GN. So I'd like to tell you a bit about like the different use cases that we have explored, which is the startup journey. We made some use cases for denoising. So basically we made like we found like a brain-inspired algorithms and figured out with the way that we want to design our chip, how much energy is this denoising algorithm gonna take, which is 0.013 milliwatt. And then with the same like accuracy, you can say, or the same like denoising capabilities. We've also been looking into implantable cardioverter defibrillators. So this is like devices that are implanted into your heart, and they give your heart a shock when required. And then the problem with these devices is that sometimes it shocks people by accident, which is of course not very good if you already have problems with your heart. So if you deploy algorithms on a device like this, you can reduce the amount of inappropriate shocks. So we were like looking into, okay, how is that done now, and how would it be able to be done? Here you can see some of the classifications. And so, they use these like high wavelet transforms. So we tried to look at, okay, how much does it look they are using it for a custom ASIC? It's 1.9 milliwatt. If we use Phoenix, our chips, we will simulate it to be 1.2 milliwatt. And if you use a microcontroller, it's 166 milliwatt. So these are like cases where we're like exploring how do we position ourselves from others to find a good market opportunity. We've also been exploring filtering. So this is filtering of glucose data. If you are having, this is something that can be used for insulin pumps. So it might sound like a lot, but it also is a lot when you're in a startup and have to find the right place to start. So basically what we want to do with our product is we want to offer a chip that can be bought easily, that can that offer this like low energy consumption with the algorithms and have high flexibility in the algorithms that you can deploy. And here is some of our partners and letters of intent that we have. among others, Danish Sound Cluster, where we've also been a part of an accelerator. And then we've just been a part of the Danish Tech Challenge, where the winner was found yesterday, who were someone who were curing cancer. So congratulations to CareDNA. We are in the neuromorphic chip market, and it's a market that is growing with 104%. It's a $2 billion market, 2 billion kroner market. So it's a market with a lot of opportunity. And basically, we are like separating ourselves by making it really easy to deploy more like deterministic algorithms and signal processing, having a scalable architecture, and then of course to support these neuromorphic low power algorithms, so brain-inspired algorithms. And what is next for us is that we are finalizing our prototype, getting our patents, and then we want to start a research and development project with like a bigger corporate. So this is also like why we are like making our demonstrations now. So that's us.
Thank you very much, Anna, for your presentation. And we will hear and see more of you in the discussion. But for now, I would like to leave the floor to the next person in the panel. That's you, Dennis.
Yeah, thank you, Jeppe. Let me just bring up the slides. Let me know if that worked.
Yep, looks good.
All right, yeah, but thanks for having me. I'm always glad to talk about microchips. I brought in this presentation a brief overview of SkyCore, what we do, and I also brought in the end a few slides more specific to the topic of this webinar, specifically how we at SkyCore started our journey coming from academia and on our way towards big business. But first, introduction to SkyCore to give you an idea of what we're working on here. The main motivator is basically that everything today uses more and more electricity. One example is AI data center, which is definitely the talk of the town all over the place. But you have many other examples when it comes to electrification, where you see now, for example, our cars are driven by electricity. And basically, we are replacing carbohydrates or carbon fuels with electricity. So there's a big demand for electricity around the world. And when you dig a little bit deeper into kind of the architecture of electrical systems, you'll realize that you need to convert this electrical energy from higher voltages down to lower voltages. And that one place where that happens is inside of a data center, for example. And if you plot how much power data centers are going to use, depending on what sources you find, it's something like top 10 of countries if all the data centers were countries. So it's an awesome amount of power that gets into those data centers. And what we're working on is then this electrical conversion, so power converters, which can fit into, for example, data centers, but also power modules in other places, and convert electrical energy from different voltages between different voltage domains more efficiently and at a lower cost than the competition. An overview of SkyCore. We founded in 2021, spin out from DTU. We're headquartered here in Denmark. And the product is these power conversion integrated circuits that you see here, one example of them. And the value proposition is that we can provide chips that enable you to implement more high performance DC-DC power converters at a reduced cost. And the applications where that is needed is really the cutting edge applications such as AI data centers, where, for example, you've seen the rack power go for something like 10 kilowatt up to 120 kilowatt in a very few amount of years. So because you have to cram in more and more power into the same space, integration is a very, good way to achieve high performance in such a market. We also work with power module manufacturers to integrate our chip into modules, such that, it can go into all sorts of applications, including industrial applications. I just brought some, how to say, pictures of everyone here, so you have an idea of who we are. So we have the founders on the left. We are, I would say, mixed bunch from Spain, France, and Denmark. And we also have some people on our board and advisors here from a lot of Frenchmen, actually, but also some people here from Denmark and also from the Danish chip industry. I also brought the business model slide because I think that's also relevant probably for this webinar, that we are a fabless semiconductor company, which is basically the business model where you make chips, but you don't own the factories, which is a very common and very popular business model today. So we mainly focused on the design of chips, generating IP, so patents, for example. And our main costs are then salaries, patent applications, tools, so software. And we don't have to have a lot of CapEx investments to building a fab because it's simply so expensive that it's kind of out of reach for most companies. Here a more detailed example of how the power structure looks, for example, inside of a data center, but it could also be other electrical systems where you usually start out with a high voltage. Let's see if I can point, maybe not. Yeah, well, we start out with a high voltage at the input, and then you convert it down. At the end, you need something for the GPU, which is around 1 volt, a little bit below. And you do that in steps. And we kind of found out that, okay, the 48 to 12 volt step, it's part of the, how to say, power conversion chain that happens directly on the board. It's a very, how to say, it's a place where you need really high performance because any waste you have here, it will turn into heat and you need to evacuate that heat out of the data center, and that's very expensive. So that's kind of where our demonstrators are focused. And I managed to not make this annotation work. Let me just see if I can get my slides back. There they are. And let me just clear this. Yeah. So yeah, I'll just briefly show you some examples of the products we're working on. So here is one of them, which can implement a very high performance DC-DC converter. And you see here at the bottom an example of a demonstrator board where you have our chip together with a few power transistors and then a bunch of capacitors. This is a test board. So if you can actually cut out around half of those capacitors in a final product. And we also work both with gallium nitride FETs and silicon FETs, and they have different trade-offs, and you can get different performance with them. And finally, we also have a pilot project running on active cell balancing, which is another application. Basically, you can make big battery packs last longer if you have active cell balancing in them. And chip design is one good way to make that happen at a very low cost. All right, I've finally brought just a few slides to give kind of like some input to the discussion later maybe, and also just in general to this webinar. So how to start a company? I believe you need people, time and money to make that work. And as you see here, we 4 people, co-founders who founded Skycore back in 2021. And before that, we were at DTU, which is a common way to kind of get the idea that you want to start a company. And we rely a lot of some grants that are available. There's probably also grants at other universities like Aarhus University, I'm sure, to kind of get some research turned into an innovation project with the goal of spinning out. And then you get an IP agreement with the university and you can use the IP in your business. And that happened back in 2021. And from there, you can also get some support from Innovation Fund Denmark, which we did. And also, of course, you need to get out and get private investments, most likely. I also just very high level put some points here. When does it make sense to make a custom chip? Because just because it's the talk of the town, it's not necessarily a good, how to say, reason to make a chip. So I just put here, I think maybe they will be distributed later, the slides, so you can read them yourself. But they don't need to have some kind of unique requirements that you cannot meet with just off-the-shelf components. And often you can also get very high power efficiency, also as Anna showed in her presentation. And also I know the hearing aid companies, like they need very high power efficiency. So that's why you go and make an ASIC. And of course it's small because you take a bunch of electronics and put it into a chip. It's a microchip after all. And if you have a very specialized, I would say we want very many different features, which is for example, the case in a Class D amplifier where you both have some power and some signal processing and so on. And you want to integrate it into a single chip, then that's also a good reason to do it. And finally, if you have the very high volumes or very high value product. And I also brought just a few examples to give you an idea. I think maybe some people in the audience are actually part of the Danish chip industry. But here I just took some of the companies that I have encountered on my way through the Danish ecosystem. And I didn't even filter for audio here, but most of it is actually audio. So I think that's very fitting, of course, for this webinar. But you can see here all of these examples are applications where you need some kind of very specialized feature set and also low power, for example, for hearing aids and microphone front ends. I also put existential AI, but it didn't fit into any of the boxes, Anders. I'm sorry about that. But maybe after your talk today, I can update the slide and make a new box for you there. Yeah, that's all. I'm looking forward to the discussion later, and please feel free to reach out to me if you have any comments or feedback.
Thank you very much, Dennis, for a great presentation. Next up is Christian Westmark from GN Audio, PhD and manager at Analog IC Development.
Right. Let's see. Yeah. So I think it's really interesting to take off where Dennis left, talking about when you should make a chip, and I'll get a lot back to that. But my general focus for this presentation is from the business point of view, trying to see if you're not a small startup or if you're actually established, when should you consider making chips there? I think we already covered the introductions, but to sort of justify me as a representative from big business, I work at GN. More than 155 years old company, and we have more than 7,000 employees worldwide. And even though it's not Apple or Samsung or something like that, we're pretty big by Danish standards at least. We do electronics in medical grade hearing technology, professional audio video solutions, and some consumer applications, including gaming. And we have quite a few different brands, so we actually produce a lot of electronics. But this story is going to be about how do you navigate this chip environment and figure out when it makes sense to make your own and when you should consider to buy them instead. I'm going to take an application that is very close to what I work with and is one of the things that GN is known for, our hearing aids business, where we, as seen here on the slide, you have a hearing aid. If you dig a bit deeper into the technical stuff, you can see there's a battery and an orange fold here, which is actually part of our electronics, which is a PCB assembly with another smaller PCB put on top here down in the orange rectangle zoomed in here. And what I want to say with this slide is basically just that everything is really small. That's the first point. You can see these are 0.1005 components. And to those of you who work in the electronics industry, you'll know that they are 0.4 by 0.2 millimeters. So this whole thing isn't that big, and you can easily imagine stuffing one of these things inside your ear. So we have some really special applications and requirements here. Despite that, you see two different chips on the top. And one of these, once again, for those of you in the electronics business, NXP, is definitely not something we make ourselves. That's something a big known vendor supplies to us. But this other chip is something we make ourselves. And why are things like that? Why do we do it that way? That's one of the things I'll try to help you understand and hopefully make it more clear to you whether you should start designing your own chips or what you should do. So I made a very dumbed down version of some of the things that Dennis also talked about before. And basically it comes down to make or buy. So whenever you have an application that you want to support, you can use this flowchart to at least do the first screening for whether it makes sense or not. So the first thing is, of course, you expect crazy high volumes. If that's the case, and you can afford a long and expensive development, then it's probably a good idea to make a chip. And crazy high, that's many, many, many millions often for that to make sense. That's not the case for GN. We primarily use it for hearing aids, and although we make millions of hearing aids every year, it's not big enough to justify it by itself. So when we go to the next box, do you have unique requirements and or skills? I also think Dennis touched upon this. Some of the things he talked about was power efficiency and size. And those are definitely things that make sense for us, but also the fact that some of the applications that we use the ICs for are actually areas where we think we can also achieve better performance than we could by getting off-the-shelf components from other vendors. And then, of course, we're fortunate enough to actually be able to afford a long and relatively expensive development. And I also touched upon this, that if you make your own chip, it can be pricey. And then just for the heck of it, I added this last one. Do you have money burning in your pocket? Yes, then make a chip. This is what I like to call the academic route. Right. An example for GN, as I talked about before, shown on a product level here, where we see a diagram of a typical hearing aid. Basically, you have some microphones, you have some analog to digital conversion, a digital signal processing unit, then you have a digital to analog conversion again, and some audio amplifier and a loudspeaker. That's the base thing. Among these things, we believe we are really, really, really good at making low power, high performance ADCs. So we make that ourselves. We also believe that we are really good at making DSPs. So we actually make the own digital signal processing units. We also make ultra efficient power management. But the example I showed before with this big chip on our hybrid assembly here and another chip here, that's actually the radio side of things. Once again, we have this chip we develop ourselves because we are really good at doing ultra low latency between communication, that is from one ear to another ear, which allows advanced sound processing. But on the other hand, we don't believe we're the best in the world at making low power 2.4 gigahertz or Bluetooth radios. So there we decide, no, we're just going to buy that instead and focus on what's our core business. So that's something you always have to keep in mind, because developing these things is expensive and can be difficult and long lead time. So choose where you want to invest your power and money. So once again, coming back to these different fields that GN operates within, even though we have all these different things, gaming, video and audio for professional use and all that stuff, we actually primarily make chips for our hearing aids industry. So I think that that's an important message to send. Don't just make chips because you can and because it's the talk of the town. You need to consider whether it makes sense for your application as well. And we do that on a continuous basis and always try to figure out where we should buy something from new smart companies or existing big companies, or whether we should actually try to invest in critical IP for ourselves. But yeah, I also look forward to answering any questions there might be from those of you out in the industry considering going into this, or those of you who want to start a startup or anything. But that's all I had for now.
Thank you very much, Christian. And before we go to the discussion, we have one person left in the panel who has not done a presentation yet, and that's you, Farshad Moradi. So please take it away.
Can you see my screen?
Yes, thank you.
Excellent. Yes, thank you so much, all of the other speakers, and thank you for having me and arranging this. This is really great. What I'm going to talk here probably cover some of the topics here, but from the, let's say, academic perspective. So I will tell you what was my journey here to Denmark, just to give a highlight how difficult is the life of an academic person, and then where we are now. So yeah, I mean, I did my PhD in Oslo, Norway. Part of that for 1.5 years, actually, I was at Purdue University in US. Then I joined Aarhus University. When I joined here, in the first day, they told me you have to teach an IC design course. The first day, I mean, it was like I had almost 2-3 weeks to prepare all the slides and so on and so forth. And there was no IC tools. There was no kind of simulation tools. There was only I was given a laptop and a desk, which was with an office shared with others. So then through this, let's say, more than 10 years journey, what we have been able to do is not a self-compliment, but I think it's impressive what we have done. So we are part of around 500 million DKK projects, both international and national projects. We have graduated 9 PhD. In our group, also I've been co-supervision of several others. So you can see that where they are ending. So some of them are in IMEC, Apple, WSA, some are ending in university, some in the startup, some are doing postdoc in Stanford and Novo Nordisk. So you can see a range of different industry. So we have postdocs. Postdocs are ending to industry and academia both. And currently we have around 8 PhD, and we have been able to graduate more than 60 master and bachelor theses within IC design, which are ending into different companies. But unfortunately, the ecosystem around chip design is not very strong in this area that I'm living at the moment. And even, I mean, in the national scale, if you compare it with other places like Belgium or Netherlands or Switzerland, so we are still lacking these types of companies to attract our talents. So this is my team, including assistant associate and PhDs, postdocs, and also senior IC designer. So our focus is mainly on IC design, but in academic world is a little different. I mean, what you mentioned, Christian, about the spending your money. So actually, we kill ourselves to get some money and then spend it on some radical or crazy idea that we think that it can make a big impact. And that's where we are ending. So a lot of European projects on future types of emerging technology, and also we work on in some industrial application. So I will give you kind of 3 pillars of research that we are doing. I mean, if you look at the hearing aid, so what you mentioned, both of you guys, I mean, this power management unit or these DC converters are quite important. We are talking about the sensor data processing, that you need an interface and do the processing part. Then you have the communication part. And what we are focusing here at Aarhus University is kind of 3 pillars. So we work on sensors and interface, so different types of sensors for biomedical application or for industrial application. So the difference between these two is that we have a strong pillar on biomedical. It can be wearable or it can be implant. But for industrial application, also we are looking at the industrial challenge, and then we work on sensor and interface, doing mainly analog mixed signal IC design. We work quite a lot in neuromorphic computing. I mean, this is where existential AI is working, and we do different types of computing, analog, digital, or hybrid types of neuromorphic computing. And also on the power management side, also we work quite a lot with energy conversion and energy harvesting, battery management, and so on and so forth. So we design quite a lot of power management chip. So every year, I mean, we fabricate 4 to 5 chips through different technology nodes. Mainly, we are working on 65 and 28 nanometer at the moment. This is just one example of a crazy idea, putting a small implant in the range of, let's say, 500 micrometer cube into the brain, powering it using ultrasonic waves, then turning on an LED, which is driven by an AC-DC converter, and then power regulator, the power management unit, generating this pulse in this small device using ultrasonic, and then putting in the brain of, let's say, in ex vivo, and then later on ending up in the brain of an animal, so for treating Parkinson. So I understand this might not be now in the market, but we see some companies are growing quite fast within this area. So on the computing side, we are working on different types of computing, both analog and digital. So here is just one example of our chip, so which is a 16-core processor that can be applied for different types of signals, especially when real-time data processing is quite important. And each of the core has 256 neurons. So you can, if you are interested in making a network with 4,000 neurons and 1 million synaptic connections, then you're welcome to contact us and we can test your idea with our chip. Then we built also another chip with a focus on more, let's say, not biomedical, but a small scale type of real-time processing. Then we built an 8-core processing unit. We call it the Spire chip. And each of the core had 256 neurons. This is a kind of reservoir computing. And then this chip, not compared to the other one, has learning, on-chip learning. So meaning that the system learns by itself. And you can do it in a supervised way or unsupervised way. This work is not published, but soon, so the measurements are done. And I think we are going to file a patent and also publish it very soon. Then we looking at the industrial applications, so you can see that we also work with something that it doesn't look like this tiny chip can go and make a change. So for example, in the bridge and tunnel, we are building a full system on system on chip in a way that can get the data from concrete and monitor corrosion, process the data, and send a signal, communicate the data, saying that, hey, there is something going on here. And the interesting thing here also, actually, we are harvesting energy from corrosion itself. So if you look at the full system, so you have the sensor, we have built the sensor, we have made the sensor interface, we give the data to a kind of a processor, and then we communicate the data. So you can extract different types of information. Another interesting project that we had is that called PipeSense, is funded by Innovation Fund. So you can see different types of calls. So EU, more like radical technology, but Innovation Fund is more on applied side. That's where we work closely with industry. And then what we did was we built a fully system on chip, which is harvesting energy from twin pipes because they have temperature gradient, powering the full system, and then processing data on the edge, and communicating this data with a drone or any external hub. And these have been tested in fields also. So, and these are more like European projects. So we are also looking at a very specific computing type of system that can come maybe in 10 years, where spintronic devices are in kind of nanoscale device. When the current sums up, then they start to oscillate and they act like a neuron. So you can make a neuron with a nanoscale device. So imagine that you put millions of these small devices together and build a chip, which is not comparable with CMOS technology. So these types of technology are going beyond CMOS. So that's where the CMOS scaling ends, and then we have to move to new types of devices. So another type is another device that we are using. So we have a full power management unit. We have a full sensor interface. So we get the data from a spintronic sensor, which is like a magnetic field sensor. You convert the data to digitize it, and then you do it for processing. Or we can even get energy from RF energy harvesting using these small devices, again, nanoscale, and then do the power management unit for powering the rest of the chip. And this is a full system on chip that we have also built and patented. So it's not only about crazy research, but also we have filed quite a lot of patents, actually around 12, 13, but 5 of them has been already licensed to Cenexum, and there are 5 to 6 more that are going to be licensed to a startup focusing on sensor interface, but for industrial application. That, I mean, some of the examples I just mentioned, for example, for water leakage detection in buried pipes. And for example, Cenexum is focusing on a fully implant device in future vision. But for the first version, what we are trying to do is we want to set up this in a hospital and then process the data, giving it to a processing unit, and make a detection. And in a later stage, probably we can do prediction and also prevention through simulation. So this simulation can be ultrasonic, can be electric, or can be optical simulation. So yeah, I mean, the path that we have gone, like Dennis, InnoFounder, and then also a grant solution that we have secured some money that we are diving into this, and hopefully we can implement in the hospital. Just a kind of an advertisement about Danish Chip Competence Center, because I believe there are some companies here. We are also part of this Danish Chip Competence Center, headquartered at DTU, but we are. I mean, I hope you know about the ChipJU. I'm not going through this, but this is a nice platform. If you're interested in chip design fabrication, please contact us so we can connect you to pilot lines, so that there are some specific topics that you are interested. If you don't have access to design platform, we help you to get connected. We help you to get into some consortium within chip area and different fields. You can think of photonic, quantum, or traditional chip design. So if you are a company or SME interested to collaborate with us, please contact us. And we are talking about the total investment at EU level of $40 billion or euro. So we have a specific focus on the skills and training and also business development. You can see the percentage here. So if you are lacking some knowledge or you are interested doing some feasibility study, please contact us. We will help you with number of hours allocated to this. So you come with your specs. We tell you if this idea that you have is possible or feasible, and then we can also help you up to fabrication. So meaning that starting from design to prototyping, we will be able to help you on different tracks on photonics and CMOS, and also other types of technology like quantum. And this will be based on a paid model probably, but with a discounted price. We have already made contract with Solfilogger and Existential AI, and we are looking forward to this collaboration. We have already provided the feasibility study to Solfilogger, and hopefully we can help Existential AI for fabricating their first prototype in CMOS technology. Also, we are in contact with IDON to help them for making a chip-based indigestible capsule. And this is where we can provide our expertise within chip design. Also, we are in contact with other companies, not only these companies listed here, but many other companies. So if you have any question, I would be happy to answer. But just a little short advertisement is there will be a lot of call within ChipJU, but there were some seminars before, but there will be many more seminars coming up. So please try to join these types of seminars and make sure that you know what EU calls or what are the availability for funding your startup or SME. And feel free to contact any of us in Danish Chip Competence Center. Thank you so much.
Thank you so much, Farshad, and what a way to end the presentations here. What a tremendous offer you can give. Now, Jørn, you can put on your camera, and I will actually just leave the floor to you, and you can take it away from here.
Thanks a lot. What an impressive presentation from all of you. I think it gives a good impression of how broad the thing is, from very early startup with Anna and Existential AI to Dennis, who actually is scaling up in this business, and then again Christian representing the hardworking backbone of our industry through one of the hearing aid companies. And then again, I think it's impressive to see the amount of energy that Farshad and his team in Aarhus has actually built up over the last 15 years. Really, really impressive. And I think his perspective to this with these very wild future technologies is very important, but also focusing on the reach out to the established electronic industry with the initiatives that we have on the Chip Competence Center is, I think, the most important thing that we need to look into right now. We have some good questions from the audience already, but please feel free to ask more in here. So I will actually start from my own perspective here, because you mentioned that it's a costly process to do that. Could we have some numbers on the table if you are able to do that? And I will start not with you, Christian, because you have crazy budgets for that, but maybe Dennis, who've been on the path here. Could you try to elaborate on what is the cost to start up a ASIC project?
Yeah, sure. I can come with some high-level numbers. I think you can, how to say, it comes in many forms and shapes doing an ASIC. Because, for example, at DTU, we did many small ASIC projects. We have the Europractice Center, which can collect designs from many different, both universities, but also companies, I believe, and put them all on a single, how to say, MPW. So that's a cheaper way to get into it. I think there you're in the order of probably 100,000 kroner or something like that. At least in that ballpark, I believe. But then you don't get a whole lot of samples, you have to remember, because in general, when you think chip design, you think, you get a wafer with thousands of chips. But if you do an MPW, like multi-project wafer, you might get 50 or something like that. If you go up and get a small, either a full wafer or a multi-layer mask, it might be on the order of 1 million kroner. Like 1 to 10 million for something like power, which is not too advanced process node. And that also includes then costs for packaging, for example, because when you get if you get a wafer, you cannot really use it for anything if you don't, slice all the dices out of it and also get it packaged either by wire bonding or what we have used a lot is also wafer level chip scale packaging, where you basically package the entire wafer all at once. So I would put it in that ballpark. And then, of course, the cost of tools is a big one. Like we were fortunate enough that one of the EDA suppliers, they have a university program where you get in at a cheap price, and then once you start to make money, you pay the big price. But I know, of course, Jørn, you've also been a lot involved in open source tools, so maybe that will come up later. But that's basically the big costs. So like prototype production is like, let's say 1 to 10 million. Tools, big cost. I cannot say like specifics, but it's more than a PCB license for Altium Designer, for example, even though that's also costly, but like it's very high in general. It's also very advanced tools that you need, of course. And then you need the salaries and so on, and that's basically it. And that was kind of for the prototyping scenario. Of course, when you go up and scale up your production, you get like all the upfront costs, they get amortized over like millions of chips. So the masks that you only buy them once, right? And then it's more the wafer cost. And typically wafer cost can be around 1,000 euros for like a not too advanced process in higher volumes. Like that's at least the ballpark you can put into your spreadsheet. Also, if you look at like these foundries and look at their financial statements, you can kind of divide the numbers and get approximately numbers like that.
Yeah, and to boil that down, when you've done the initial cost, then you buy a wafer, $1,000, and you split that up into the number of devices you actually do on the wafer, and let's say that's 2,000, then you get back to a known good buy die price around 50 cents. Then you need packaging, testing, and adds up 25 cents or something like that. So you end there, very cheap. But that is also something that you plan to go out in high volume to motorize and get the money back in this way.
Yeah,
thanks a lot.
I think I would just add, an asterisk to this, and that's of course within the stuff I'm working on, which is power, like higher voltage stuff. Like we are talking above 100 nanometer processors, and of course when you go down in lower nanometers, for example, probably the stuff that GN is working on, it's a very, very different cost structure. But this is, I think you can also do a lot of good audio products in a process like we are working with. So I think for a wide part of the audience, these numbers are probably like a good ballpark. But if you want to do more like advanced digital processing where you need like very low nanometer nodes, it could be 100 million instead of 1 to 10, right?
Yeah. So basically, cutting edge technology is very expensive. It requires that you have Apple Meta budgets to run on these things. But for what we do, power, audio, you can get away with something that actually can handle the power, and you don't need that a lot of digital number crunching things. That is actually more suited for the cutting edge technologies.
Yep.
I have another.
Sorry, just a short comment, but let's not scare the ones that want to do a startup. I mean, we are a university and we are prototyping every year, like in 5 rounds, MPW, and also there is another program. It's called Mini ASIC. So if you have a smaller design, you can buy a smaller area, not 5 by 5, but 1 by 1 millimeter square. For example, it costs 10,000 euro for 28 nanometer, which is a kind of advanced node. But if you go to 180 nanometer, is 3,000 euro. So it's not much of investment if you want to have a proof of concept, especially if you work in analog domain. But for digital domain, yes, it costs 10,000 euro per millimeter square, and then some cost of packaging. But I doubt if you just need to jump to wafer level for now. Just if you have an idea, you want to prototype and make sure that, okay, this adds a lot of value to your current product that you're using off-the-shelf component. I think you can easily do it with a small investment, and you're very welcome to contact the Danish Chip Competence Center for this. We will be able to definitely help you and then give you a better estimation of the cost and budget for such activities.
And also, Dennis mentioned that the open source environment is actually moving very, very fast. We only have had open source chip design possibilities within the last 4 years, and we are moving fast there. So I see, especially for the legacy nodes, so what we talked about here is actually getting almost down to zero cost for taping out on some of the initiative that was done. There was the Google initiative with the Skywater 130 nanotechnology, and we have the tiny tape out that gets even cheaper in this way. And this is a good way to start to dive into the chip design and get a feeling what's about. I have another question from Tobias, and he asked about how to get into cooperation with the industry for instance, master thesis or just like student jobs. Anyone who wants?
I can chip in. Like for example, we have a very good collaboration with DTU. Have hosted several bachelor and master projects, and also have student workers working with us. Like I myself was student worker back at Mirrors Audio when Jørn was also working there. And I believe that was really a great experience, and I definitely want to pass that on to as many students that we can afford to hire. I see DTU, I think they changed the rules a little bit now with special courses, so it's a little bit harder for us to host students. But definitely bachelor master projects, we are always open for it. We just had the chip day at DTU. I think that is one place to kind of meet the companies in the chip industry. That was yesterday, so now we have to wait a year for the next one. But I mean, there are different events around the place where you can meet the chip companies like us, and I think that's one way to get involved, because it is a pretty small community. So you kind of, how to say, sometimes you have to get a little bit lucky, like who you bump into, and how to say, on your way into the industry.
I think also that the Chip Competence Center can be a good facilitator for this as well.
Definitely.
To cover up or embrace the full community. And again, I will state out that the DTU Chip Day that was held yesterday is also a good opportunity, not only for students. I know it's meant for that for now, but it would be nice that we next year do that so that we can also invite people from the industry wondering if they should go into chip design and come and meet. We represent like 20 companies there from very, very broad industries, all doing ASICs at various levels. So that will be a good opportunity, but we'll take that until the next evaluation. I have another question from Mickey. So he asked for Christian, you from GN. So is IP something that you sell? Imagine that you have a company within another business. Could they buy IP from you?
I doubt it. I can say it's not something we currently do because we want to keep our competitive edge on the stuff that we are really good at. From a business point of view, it might make sense, and we do have some strategic collaborations with some large companies, but usually within other domains. Cochlear is one of these examples where they do some cochlear implants, and we have a Smart Hearing Alliance where we collaborate with them, but we don't as such sell IP.
Yeah, thanks.
We do buy IP though.
Yeah, so if you have an IP, there's customers there.
Yeah.
We have another question, and I think we need Farshad to ask or to answer that. So Raman, he asked, what about MEMS? Is that something we have on the line card?
For the under the competence center, yes. I mean, I know Klaus is in the audience, so please contact the center leader or contact me, and we will link you to the right people for MEMS and fabrication at the DTU Nanolab.
And can you please elaborate MEMS? What is MEMS and what is it used for?
Yeah, I mean, microelectron machinery system. So it's just micro scale types of device that can be used for sensing, most probably, or it can be used for energy harvesting types of application, or many other applications. But yes, we do cover this.
Yeah, and that's a follow up from Raman, but I think it's important for him to reach out to the community, DTU Chip Competence Center, and there is actually a lot of activity in this area within DTU Nanolab, where they actually produce them. We get training in the field as well.
We also have a good example in the industry, right, with Sonic Edge, who has a new product based on MEMS technology. So that's also very relevant for the audio industry.
Yes.
Yeah, and to elaborate on that, so that is actually a technology that requires that you do CMOS design very close to the MEMS device to actually produce something that is unique to a speaker in the field of a speaker that we haven't seen before. So I think one of the very important things that we should do, and we are able to do here in Denmark, is to try to couple different industry to each other, because there might be something from the MEMS industry and the electronics industry that need to be worked on together to benefit from this. And we see the same trend within cryogenic chip design. So the Chip Competence Center had a session on this 1 month ago where they invited everybody from quantum hardware at a seminar at DTU, and it's pretty obvious that there will be a focus in the near future to work on cryogenic CMOS design, and that is a field that has not been very much researched or with no commercial offers yet. So, but I think that's a place where it fits very good into the Danish chip design industry that takes very hard questions or problems and actually are able to solve that. We've done that before. RF for hearing aids, RF for cell phones. Yeah. Let me look through the questions here again. And then again, if anyone from the panel would like to put a comment on what you heard until now or raise a question, please feel free.
Just one thing that someone asked about whom to contact and who is who in the center, the Danish Chip Competence Center. So now I'm physically here, but there is another person here. But you can go to the website of dkcc.eu, and there you can just reach out to us, or you can directly contact me, and then I link you to the right people. So at the moment, I'm the representative of the center here, but Klaus is leading the center, and the headquarters at DTU. So, but if you go to the website, just contact to any of us. We will be glad to help you if you have any question.
I have another question from Klaus Romdal, who asked for you, Farshad. So, if you have patents at Aarhus University, could that be shared between DTU? So, is there a legal?
I mean, some of them are already licensed to the company Sanexom, but the rest are again owned by Aarhus University. I mean, all these legal things. It's something that needs to be discussed with the legal office and TTO, the Technology Transfer Office. And I can answer some, but I think it's better to be through the Technology Transfer Office and the legal office at Aarhus University. But I can, if you contact me, I can link you to the right people, and then we can take it from there.
Thanks. Anyone else from the panel would like to put a comment to everything or to anything they heard before or here?
Maybe I would like to make an addition to my previous statement about this selling IP. I just saw that the question was about selling to non-sound companies. And what I said was that we'd like to keep our competitive edge and not sell to competitors or others that might be too close to what we do. But I still don't think we would sell to non-audio companies, but I think that the specifications for our ADCs in this case, they are too specific for audio applications for them to be relevant for others. So I don't even think they would be interested in buying them, depending, of course, on what they want to use them for, but they're very specific in bandwidth and power consumption and so forth. So there probably wouldn't be a very good business case in it, even if we wanted to sell.
We have in our company also some discussions about this, about like being IP or like physical chips, like what is the best way to go to market, because it's like two very different ways to like get into the market. And so where you go and see like other companies, they can maybe like actually make a lot of money from selling the IPs, because obviously you don't have to like have the same like production cost and like that. But it's also like it's making your sales cycles much longer. And so I've been talking with quite a lot of investors who are like, first, like it's your sales cycles are longer, but also as Christian says, like you are kind of sharing your IP then, which might be what is making your company valuable. So it's also some discussions that we are having at the moment.
And again, I could again point out that in the open source community, we already have a lot of IP blocks developed. It might not fit into the process technology you are looking at, but at least that's a good starting point, because there, like in software, a lot of things has been developed, tested, or fabricated, tested with sponsorship from Google and other companies that moves in this direction. And again, I would stress out, please contact the CHIP Competence Center, because they have full visibility into what exists already. If it's something that has crazy requirements, then that's hard. But if something that is not stressed in this way, but important for a company's product to be small or power unsensitive, then there are possibility to look at what's already designed there. So there's a question, so what an overview of MEMS speakers companies which is coming up from hearing aids. I think that was for Christian. I don't really understand that, but I guess what Christian, can you elaborate on what kind of MEMS speakers you use in hearing aids? I know you probably have the numbers that we ship more than 10 million hearing aids from Denmark. Each of them have at least one speaker. Could you elaborate?
Yes, that's true. And it's going to be a quite short answer, or I'll extend, of course, but none. So we don't use MEMS speakers. We use something called balanced armature drivers for the hearing aids. I don't know the details of why we don't use MEMS, but I do know that the MEMS ultrasonic alloy stuff from Sonic Edge, for example, that's too power hungry. And I know that from other MEMS applications that I worked with previously, that usually driving MEMS speakers or MEMS stuff in general requires quite high voltages. So it might not be easily integratable in the current hearing aid setup we have. But I gotta admit, I don't know the details of that, but we don't have any currently.
And can you elaborate on other MEMS stuff that you have in the hearing aids? Because what about your microphones? Yeah, so on the microphone side of things, there's a big vendor that delivers to all tier 1 customers and many others in the world that used to be, well, they used to have a Danish office at least called Knowles. Of course, there's some MEMS microphones that we use there. Also don't know the details, but we do make the amplifier part for the MEMS microphones we get. I don't know if there's any others really that we use, still a bit outside my domain. But again, the point is that we are using MEMS microphone because that is the state of art for microphones. And again, you don't only use one, you probably use a couple
Definitely.
in each device there.
Yeah.
Then we have another question from Mikkel Bering. So, Christian, you mainly focus on the analog, but could you elaborate on the challenging when moving into complexity and cost of, for instance, 10 nanometer nodes and below? So how would you keep up with that if that's what you're looking into?
Sure. So first of all, I'd go back to my flow chart and say, do I expect a crazy high volume? Then again, I'd say, no, I don't. Then I go down to the next one. Do I have crazy or specific requirements? Yes, we do. We want to keep things very low power. And even though we do have a lot of digital electronics, which is usually what drives the technology development and down into smaller feature sizes, smaller nodes, there is a limit to what you actually need to process or what you can process with the given power you have and the activity in the digital circuit, which means that at some point in time, it doesn't make sense to go down in process node anymore. That's more for high performance applications. So we would probably never, I don't know, at least as it looks now, consider 3, 5 nanometer or any of those super small nodes. So we'd stay at a power optimum where leakage doesn't start to dominate too much. But of course, still going down into the advanced nodes, 10, 20, 30 nanometer, that area. You do get some challenges. Complexity of the design becomes higher. You need to pay for more expensive licenses to actually be able to verify your design. So how do we handle it? We really try to make a feasibility study and see, is this really something that's worth it for us? If it is, then we take on the risk of the complexity, and then we try to see if we can develop what we set out to develop. And of course, if you succeed and you made the right decisions early on, then a couple of years down the road, you probably have a superior hearing aid.
Just a question from me too. So then why not hearing aid company in Denmark in general dive into more scale? You mentioned 2, 3, even, I mean, I'm talking about 10 nanometer, for example, or 7 nanometer, which is going to be, okay, one of the pilot line actually is to scale from 10 nanometer to 7 nanometer. So why not establishing collaboration with universities to explore this, at least for some specific components? This will be a kind of a cheap path in comparison to like big investment on a specific technology node. I mean, just evaluating, okay, if you make a small core for a specific application in 10 nanometers, 14 nanometer, what would be the results? If it's 50% better in terms of energy efficiency, I think then it helps the hearing aid companies to say, we have the lowest power, blah, blah, blah. But if we just say, okay, this is expensive and so on, so we're not diving into it. And if there is a new, let's say, company coming from US or other places, they're already working on 5 nanometer, 3 nanometer, then how this will affect the hearing aid business in Denmark? This is, I don't know, I'm sure it's a concern that probably is already there, but would be an interesting question that maybe managers can also think about it.
Yeah. I mean, we do, of course, spend a lot of time investigating it ourselves, and I'll get back to your question about the university collaboration afterwards. But first of all, I think it's important to understand that when we develop, for example, the DSP, which is probably what drives what would drive going down in Node.
Yes.
We do also develop the compiler and all the firmware, software, everything that runs in it, we develop it in-house. So just defining a use case that's representative of what you expect to see in a product 5 years out in the future is quite difficult. Of course, we have people working on that all the time. And based on whatever compiler and architecture of the sound processing unit and everything, we do evaluate the power consumption of different processes. But doing the actual evaluation of the process once you have all the other things in order it's not easy, but it's not a huge task. So I think there might be room for some more interesting collaborations with university. And as everyone else, we have limited bandwidth, and we have people working on deliveries that need to be done in time in order to get products on the market. Yes. So every time we engage in collaboration with others, whether it's a larger formal collaboration with university departments or if it's individual students, we need to think about which resources is this going to take. Obviously, we want to use some resources from our development teams and sort of leverage their time. maybe it's an interesting area to look into. I don't know, but yeah, I think there are others that could be more interesting.
Yeah, and I think the point here is that the home-driven sub-nanometer technology design is very expensive for in size of Danish companies, even our hearing aid industry that has
Definitely.
high volumes. And when we say high volumes, that's maybe 10 million devices a year. It's simply not feasible from a budget point of view. But I think I hear an invitation from Farshad and the university area that try to come up with something where you can do this 7 nanometer, 5 nanometer number crunching engine, use the chiplets strategy that you use at the very large chip designs, scale that down to the hybrid model that you use in the hearing aids. So, and Christian, maybe you can elaborate on this because you already have a hybrid. So you actually do a PCB where you mount different chips on. You could actually do one chip where you mount a super sub-nanometer technology that I can actually do number crunching for you there.
Definitely. It's a technological possibility, but an expensive one. And yeah, maybe to elaborate a bit on this hybrid, we do use multiple process nodes. I'm not going to tell you exactly which it is, but we do use some in the 10s, 20s, 30s nanometers. We have a 28 nanometer process in our existing hearing aids on the market right now. And then we have some older technologies up to this 180 nanometer benchmark and something in between, depending on the the application of the different chips we have. So we do this feasibility study all the time, figure out which node is best suited for the specific application that we're trying to implement.
And I think that the people that are aware of Moore's law actually and looked into that also seen that Moore's law actually died 10 years ago.
Yeah.
10 years ago, we hit to 28 nanometer technology. And since that, the transistor that you put on the chip has actually become same price or not cheaper as we're used to with the scaling factor that we used to. So we add more transistors on the platform going into sub nanometer technologies, but again, they got more expensive. But this is a game that you need to play when you are looking into more number crunching this way. So it doesn't scale, and it doesn't scale with cost either. So that's also the concern that Christian maps out here. We are very close to ending up here. So if anyone have a last minute question, let me know. If anyone from the panel would like to do something, then I have another question I'll look into here. So please feel free. So we have a question here. So how do you start building a team for ASIC development here in Denmark? How many people do you need? And does the small community in Denmark make it easier or harder to find expertise needed for this? That's a question from Matthew. Anyone from you panel would like to answer?
I'm not sure if I understand the question. So what does it mean, ASIC development project? Maybe.
Yeah, I think you can elaborate what kind of, is it hard to find people within this area?
Yes, it is. It's super hard because I mean, especially in academic environment, is very difficult, and this is what we are challenged somehow. They like to go to industry because of many reasons. But again, I mean, we have great talents here, trying to keep them here, begging them sometimes to please stay here, don't go anywhere. But it's a tough time for academia to keep the people in academia. But I mean, if we have a strong collaboration with industry, I'm sure that both sides will benefit from that. So if you have a person like to do an industrial PhD, so this, I think, Dennis, you also did that industrial PhD. So
Yeah.
that can be a good setup because they feel that, okay, they are solving a real problem. I mean, because sometimes people look at research, okay, this is like a science fiction thing. But if we build a strong tie or relationship with the industry, then they feel, okay, they belong to the community already. They are part of industry. And if they want to stay here, it's beneficial for academia because they have industrial experience. If they want to join industry, it's good for industry because they already have some experience. But we should build the community, and this is what we want to do in the Initiative Competence Center. I mean, these people, it was like 50 people joining this webinar, and would be good that we see all of these people coming to the physical workshop or seminars we have too, because then there we can also do brainstorm. We can come up new projects, a strategic project for Denmark to get into some exciting project within chip design or fabrication.
Yeah, I think I can
Yeah,
add, sorry, I'll just add some specific numbers. Like I saw the question, they asked how many people do you need? And I think like you can get a lot of work done with 5 to 10 people actually in chip design. Like even if you look at a place like GN, it's not like they have hundreds of chip designers. Maybe a question afterwards can comment on how many people they are. But you can really get a lot of work done there. And we are a small community in Denmark, but also very highly specialized, I think, in audio, low power, and power electronics in general. So if you're in that space, you can get a lot of top talent here. Like most of the talent is busy doing something else. So of course you have to, kind of have a vision or find people who actually want to work in a startup or work on a new project in a bigger company, if that's what you had in mind. But you actually don't need that many people, I believe. You just need the right people and then the right tools, of course, as well.
And I think if we look at what Farshad actually built over the last 12 years, 13 years, I think it proved the points that it is actually possible to build up the community and the talent mass and the variety of what he already did over there. And scaling down again, the last couple of ASIC projects I've been on, that has been a two-man job over a couple of months. Using commercial tools and commercial PDKs, so it's possible. Small group of skilled people to do ASIC projects in this way. And again, I think it's important that we have turn on the long lights of our vision in this area and say that it takes time to build an engineer with 10 years of experience. So the fuel that we can put into this is the new students that comes, a great ecosystem from the universities. Then we can definitely find new exciting areas where we can apply the chip technology, because it's this is what we've done for the last 40 years in Denmark. Then I think from that I'll sign off here and leave the word for Jeppe, and thanks for the audience for the great questions. Please reach out to the people you see here in the panel. I think most of them will be present at LinkedIn or anything, and then you can get them there. So Jeppe, thanks a lot.
Thank you very much, Jørn, for your very competent moderator job here today, and what a great discussion that you guys had. Just want to say thank you to all of you contributing to today's webinar. Farshad, Anna, Jørn, Dennis, and Christian. And like you said, I'm sure they are very happy to ask any further questions or coffee talks, whatever, after this webinar. On behalf of Danish Sound Cluster, I would like to say thank you very much. Please go to our YouTube channel to subscribe to our webinars, where this recording of the webinar will be available shortly. So if you missed any of the action, you can go there and watch the whole thing. Now, we at Danish Sound Cluster would also like to invite to collaboration and building a community in this chip design area. So we facilitate and fund innovation projects, and you can apply for one soon. And what is an innovation project? Well, that is SMVs, small to mid-sized companies going together and developing a marketing process or product basically together. And you can do that through us here at the Danish Sound Cluster. And you can also you can also hook up with universities like Farshad, Aarhus University, and go together with SMBs to develop an innovation project. So if you're interested in this, please reach out to our project manager, Tine Midgaard, and you can see some of our concluded collaboration projects at our website, and hopefully be inspired there a bit. Now, finally, I would like to just mention that we have a date for our annual community party at November 5th at the Royal Danish Academy of Music, where we will build relationships, we will generate inspiration and awareness in the field of audio, acoustics, and hearing. So please mark that day in your calendar, and there's going to be more info about this not too long from here. Now, thank you very much, everybody, for today. Also, you in the audience for hanging out with us for 1.5 hours this morning. So thank you very much, and see you some other time.
Thank you, everyone.
Thank
Bye-bye.
you.
Have a great
you,
day.
Forward
everyone.
to the
Thank
5th
you.
of November.
Yes, great.